What if everything we thought we knew about the universe was completely wrong? For decades, scientists have told us that space is expanding, racing outward at an accelerating pace, powered by an invisible force called dark energy. It's the foundation of modern cosmology, the cornerstone of the Big Bang model. But what if that entire picture is an illusion? Physicist Lucas Lombreser is challenging one of the most deeply held assumptions in science, suggesting that the cosmos might not be expanding at all. Instead, he proposes a universe that is flat, still, and motionless, where the redshifts we've relied on for nearly a century aren't evidence of expansion, but the result of something far stranger, particles themselves evolving over time. If he's right, everything we've built our understanding of the universe on, from dark energy to the Hubble constant, could be fundamentally misinterpreted, forcing us to rethink the cosmos itself. To understand why Lombreser's theory is so shocking, we need to look back at the history of how we came to believe the universe is expanding. A century ago, even Einstein assumed the cosmos was eternal and unchanging, and for a long time astronomers thought the Milky Way was the entire universe. That perspective shifted dramatically when Edwin Hubble studied spiral-shaped nebulae in the night sky and realized they weren't part of our galaxy, they were galaxies themselves, scattered across an immense cosmos. But Hubble didn't stop there. By measuring the redshifts of these galaxies, he discovered a consistent pattern. The farther a galaxy is, the faster it seems to be moving away from us. This relationship, now known as the Hubble constant, became the cornerstone of the expanding universe theory. It suggested that if we reversed time, all matter would converge to a single, unimaginably dense point, the singularity that marked the Big Bang. For decades, this model held up, supported by mathematics and observations, and it formed the foundation of our understanding of the cosmos. But as we'll see, the universe had more surprises in store, waiting to challenge even the most trusted theories. The first major challenge to the classical view of cosmic expansion came in the 1990s, when astronomers observed that instead of slowing down, the universe's expansion was actually accelerating. This unexpected twist left scientists scrambling for explanations and introduced the concept of dark energy, an invisible force thought to make up around 70% of the universe and push galaxies apart faster over time. Dark energy became the go-to explanation for the universe's apparent acceleration, yet it remained entirely theoretical, undetectable, untouchable, and measurable only through its gravitational effects. Adding to the mystery, the James Webb Space Telescope entered the scene and revealed ancient galaxies that were far too massive for their age, essentially cosmic infants with the mass of fully grown giants. These discoveries reignited questions about the Hubble constant, the standard measure of expansion. Different methods of calculation using supernovae, gravitational lenses, and pulsating stars produced conflicting results, deepening the cosmic divide. Webb's precise data only made the discrepancy more pronounced, leaving astronomers to wonder, is the universe truly accelerating, or have we been misinterpreting the very mechanics of space itself? Enter Lucas Lombreser, a theoretical physicist from the University of Geneva, who is challenging everything we thought we knew about cosmic expansion. According to his radical theory, the universe isn't expanding at all. What we perceive as galaxies racing away and space stretching could be an illusion, and the cosmos might actually be flat, static, and motionless. Lombreser isn't simply speculating. He and his team are reformulating the laws of physics, presenting a new framework where the redshift observed in distant galaxies isn't caused by expansion, but by the gradual change in the masses of particles like protons and electrons over time. Instead of space itself stretching, the particles within it are evolving, creating the same observational effects that have long been attributed to expansion. This model introduces a pervasive cosmic field filling all of space-time, a medium where particles form, exist, and interact, and it is the dynamics of this field, not the stretching of the universe, that produce the observed redshift. Within this framework, the cosmological constant, traditionally linked to the acceleration of space, is reinterpreted as a reflection of the field's properties, rather than a force driving expansion. Remarkably, Lombreser's equations fit observational data almost perfectly, resolving inconsistencies that have puzzled cosmologists for decades, and offering a unified explanation for phenomena previously attributed separately to dark matter and dark energy. Lombreser's theory doesn't just rewrite the story of expansion, it also offers a fresh perspective on two of the biggest mysteries in astrophysics: dark matter and dark energy. Traditionally, dark matter was proposed to explain why galaxies spin faster than the visible matter alone could account for, while dark energy was invoked to drive the accelerating expansion of the universe. Both remain invisible and undetected, raising endless questions. In Lombreser's model, the fluctuations in the cosmic field he proposes could behave like an axion field, a hypothetical type of neutral particle which would naturally create effects previously attributed to dark matter. Instead of being a separate mysterious substance, dark matter might simply be a manifestation of how this universal field operates. At the same time, the same field fluctuations could explain the phenomena we've been calling dark energy, removing the need for an invisible repulsive force. What was thought to be two separate, inexplicable forces may actually be one unified field controlling the behavior of matter across the cosmos. This reinterpretation challenges decades of assumptions and suggests that the universe's underlying mechanics might be far simpler and far stranger than we ever imagined, where the apparent acceleration and unseen mass are just reflections of changes in particle properties within a vast cosmic field. The implications of Lombreser's theory stretch even further, forcing us to reconsider the very nature of the cosmos. If the universe isn't expanding, but is instead a static, flat entity, then many of the phenomena we've attributed to cosmic motion might need reinterpreting. For instance, the redshift of distant galaxies, long considered the smoking gun for expansion, could instead reflect gradual changes in the masses of fundamental particles over time. This flips conventional cosmology on its head. What we see as galaxies speeding away might not be motion at all, but the universe itself subtly evolving on a microscopic scale. Moreover, this perspective opens the door to a universe that is far more interconnected and coherent than previously thought, governed by a single underlying field rather than a chaotic combination of forces. It also suggests that our quest to detect dark matter and dark energy as separate entities may have been misguided, since their observed effects could be inherent to this cosmic field's dynamics. In other words, the cosmos may be far less fragmented than our models assume, with apparent mysteries emerging not from hidden substances, but from the evolving properties of the very fabric of reality. If Lombreser's ideas hold up under scrutiny, the universe isn't just stranger than we thought, it's operating under rules that demand a profound shift in how we understand everything from galaxy formation to the ultimate fate of the cosmos. The reaction to Lombreser's theory has been a mix of awe, curiosity, and cautious skepticism. Some physicists hail it as a bold, elegant solution to problems that have puzzled cosmology for decades, offering a unified framework that could explain both dark matter and dark energy without invoking unseen, unmeasured substances. Others urge restraint, pointing out that the cosmic field he proposes and the changing particle masses are currently beyond our ability to directly observe or test, leaving the theory in a speculative but tantalizing space. Yet even critics admit that challenging the deeply entrenched idea of an expanding universe forces science to re-examine assumptions that were long considered untouchable. If Lombreser is correct, decades of observations and equations will need reinterpretation, and future experiments will have to look for subtle signatures of particle mass fluctuations rather than just tracking cosmic expansion. This debate isn't just academic. It reshapes our understanding of everything from the birth of galaxies to the evolution of stars and the ultimate fate of the cosmos. The idea that the universe might appear dynamic due to changes within its very constituents rather than external motion is revolutionary, and it sets the stage for a new era of cosmological research, where what we see may not be what we've always assumed it to be. Looking ahead, the implications of Lombreser's theory are staggering. If a single fluctuating cosmic field can account for both dark matter and dark energy, it could rewrite textbooks and redirect decades of astronomical research. Observatories and satellites may start designing experiments specifically to detect the subtle effects of shifting particle masses, rather than focusing solely on measuring expansion rates. The theory also invites a reconsideration of cosmic history. Perhaps the early universe evolved in ways we've misinterpreted, and structures like galaxies and clusters formed under dynamics far different from the conventional model. Beyond the technical, it challenges our philosophical perspective too. A static, yet seemingly expanding universe forces us to rethink concepts of motion, time, and the evolution of matter itself. This is a paradigm that doesn't just tweak current models, it flips the cosmic narrative on its head, compelling scientists and enthusiasts alike to question the very nature of reality. As data continues to pour in from Webb, Hubble, and future instruments, we may be on the brink of a revolution in understanding, where the universe isn't just expanding outward, it's revealing hidden layers of its own intricate underlying framework. In the end, Lucas Lombreser's theory reminds us that the universe is far stranger and more intricate than our current models suggest. What we perceive as expansion, dark energy, and dark matter could all be manifestations of a deeper, underlying cosmic field, quietly shaping reality in ways we're only beginning to grasp. This perspective doesn't just address unresolved questions in cosmology, it forces us to reconsider the very framework of space, time, and matter. While much of the theory remains beyond our current ability to test, it opens the door to new lines of inquiry and bold speculation, encouraging scientists to think differently and challenge long-held assumptions. Whether future observations confirm or refute Lombreser's ideas, the conversation itself underscores the beauty of scientific exploration. No truth is permanent, and every discovery has the potential to overturn everything we thought we knew. The universe, it seems, is not a static story written in stone, but a dynamic, ever-unfolding mystery, inviting us to keep questioning, exploring, and expanding the boundaries of our understanding.